Okay. Okay. So we're into the second to last section of this chapter that goes on to test 2, 2.8. So here we deal with the concept of a subspace. We've always been dealing with the vector space Rn, so the set of all vectors that consists of n elements. But so those are vector spaces. But now we're dealing with portions of those vector spaces that are themselves vector spaces. So that's actually the definition of a subspace that we see here. So it's not just any old subset of Rn. It has to be a subset that follows all the properties of vector spaces. Now, a lot of these properties are fairly straightforward in terms of how vector addition behaves, or like commutativity, associativity, and so forth, and also scalar multiplication, so multiplying a vector by a constant. But all of the expected rules of multiplication apply also. But not every subset can be a subspace. And one property in particular that subspaces have to satisfy is that they are closed under these two operations on vectors, addition and scalar multiplication. And all that means is if you have a subset of the vector space Rn and you pick two vectors in that space, then their sum is also in that space. Also, if you take a vector that's in this subset and you multiply it by some scalar, then that too will also be in that set. So if these two operations keep vectors in that set, then we can call it a subspace. So what that means is, for one thing, the zero vector has to belong to the subset. So any subspace must contain 0 out of necessity. For example, I could choose because if x is in a set, then minus x has to be in the set also, because this has to apply for any number I can multiply it by. But therefore, 0 must be in the set, because if I have x and minus x, I add them together to get 0. It has to be in a set. Okay. So as an example, like suppose I'm in R3, so I have vectors consisting of x, y, z coordinates. If I take a subset consisting of all vectors where the z coordinate is equal to 0, that would actually be a subspace, because if I have two vectors whose z coordinates are 0, I add them, the z coordinate will still be 0. If I multiply by a scalar, the third coordinate will still be 0. So everything works. But if I could consider all vectors in R3 where the z coordinate is equal to 1, that would not be a subspace, because if I add them together, the z coordinate is now 2, so it's not in the set. So those are examples of things that are or are not subspaces. But today we're going to focus on two particular subsets of Rn that are proven to be subspaces. The first is called the column space of a matrix A. So we have an m by n matrix that has these columns, so n columns altogether. So the column space is just taking all possible linear combinations of those columns. And this is the abbreviation, col of A. Now, A is an m by n matrix, So it has m rows. So each one of these columns is a vector in Rm. So the column space, even though we're taking linear combinations of n columns, is a subspace of Rm because that's how many elements each one of these vectors has. Another subspace of interest, null A. So this is called the. I want to give the full name. Okay. So this is the null space of A. But this is just an abbreviation, null A. It's just whatever vectors you can multiply with A on multiply by A on the left. So matrix A is on the left, the vectors on the right, and get the zero vector. So in other words, another way of putting it is it's all solutions of a system AX is equal to 0. So in many cases, the null space will consist only of a zero vector. Like, what if A is an invertible matrix? Then the only solution of a system of equations is X equals 0. So that is a one and only member of a null space. So that can happen. A subspace can have just one element if that one element is the zero vector. So one of the homework problems involves, given a matrix, find a vector in a column space, find a non-zero vector in the null space. Okay. Now, a related concept that also comes up in this section is that of a basis. So the notion of a basis combines two concepts that we've already seen. The span of a set of vectors, like we see here, and also the notion of a set of vectors being linearly independent. So suppose we have a set of vectors, n vectors coming from Rn. So the number of vectors has to equal the dimension of the space you're pulling from. So this set of vectors is a basis for Rn if it spans all of Rn and it's linearly independent. So a basis can be used to describe all vectors in the space in a unique way. So because they span Rn, these vectors can be linear combinations of them to describe a whole space. But because is linearly independent, that means that none of these vectors are redundant. So it's like a minimal set of vectors that can be used to describe the entire space. So any basis for Rn has to have the same number of elements. It has to be n. And that's actually called the dimension of a space. It's how many elements a basis must have. So, for example, if you're in R4, if you want a basis for R4, that requires 4 vectors from it that are linearly dependent. No more, no less. So some of the problems deal with having a given set of vectors, and the problem asks, do they form a basis for whatever space they come from? So you can think of these vectors as being columns of a matrix. So I have a square matrix, and we're examining these n columns. So how do you know if the columns form a basis or not? So there's different ways to tell. So they have to be linearly independent, and they have to span Rn. So these are two properties from the invertible matrix theorem. So if these columns form an invertible matrix, then you can say that the columns form a basis. And then it's if and only if situation. So given n vectors, if you want to know if they're a basis for Rn, there are many ways to tell if they form an invertible matrix. So you can apply any one of those criteria from the invertible matrix theorem to determine if they do in fact form a basis. And we'll see different ways of using that in this section. All right. So first, working with the subspaces I talked about earlier, the column space and the null space. Here we have this first problem. Here we have three vectors, v1, v2, v3, and then we have some other vector p that's given. So the question is asking, is this vector in the column space of the matrix formed by these three columns? So we take v1, v2, v3, slap them together to get a matrix. Is P in the column space of this matrix? Now, so what that means is P must be a linear combination of these vectors to belong to the column space. But that's the same as saying that this system, AX equals P, must have a solution. So what we can do is what we've done before. We can go ahead and work with the augmented matrix. So these three vectors plus P as a fourth column. Okay, so I just added P on the end here. So we could just row reduce this like we normally would. And if this augmented matrix describes a consistent system, that means that AX equals P has a solution. Therefore, it belongs to the column space. So these statements are equivalent. P is in the column space of A if and only if AX equals P has a solution. Put this on a new page. Okay, so what we can do is the usual row operations. All right, so here we have a convenient 1, so we can add 3 times this row to this row to eliminate this element. And this is what we get. Notice that we have these two rows of a matrix, 2 and -2 here, 4 and -12 here. They're not parallel. So when we perform the next row operation, to eliminate this element, so we take twice this row and subtract it from this row, then we get something non-zero here. So we have a pivot position in every row, every column. So 1, 2, and -8 are pivots. So we see that the system is consistent. So this vector P is in the column space. So that's all it takes, row reduction to ensure that the system is consistent. To tell if a given vector is in a given column space. Questions about that? Okay. Here's the opposite problem. We're still given 3 vectors in the form of column space, form of matrix, and then this vector P. Now I want to know if P is in the null space. So that's actually a little easier to figure out because we define the matrix, these 3 vectors as columns. Now P is in the null space if of this matrix A, if A times this vector is equal to 0. So we just go ahead and carry out this matrix vector multiplication. So So if we look at the elements of P, that's 3, 6, and -2. So matrix vector multiplication is 3 times the first column plus 6 times the second column minus 2 times the third column. Just work out what that is. Okay, so there's 3 times the first column, and then 6 times the second column, plus or minus 2 times the third column, and then we work out what that is in the end, and we get this vector, which is definitely not the 0 vector. So because A times P is non-zero, that means it is not in the null space. So given a matrix A in terms of its columns, if you want to know if a given vector is in the null space, just carry out the matrix vector multiplication. And if you get 0, it's in the null space. Otherwise, no. Okay. Here, problem goes in reverse. So in the previous two problems, you were given a certain vector, and that's to determine if it belonged to the null space or column space of a given matrix. Now the goal is to find vectors in those spaces for given matrix A. So to find a vector in a null space, we have to find a solution of AX equals 0. So, okay. So find a vector in a null space of A. Just find a non-trivial solution of AX equals 0. Okay, so for that, we can perform the usual row reduction. We can see if we have any free variables. Now, actually, we know we are going to have free variables because we have only 3 rows and 4 columns. Anytime you have more columns than rows, you can't have a pivot position in every column. It's not possible, so you're going to have at least one free variable, and we can use that to get a non-zero solution. So we know it exists, but we still have to find it. So for row operations, here we can take twice this row and add it to this row. We can take 3 times this row and subtract it from this row to eliminate these entries in the first column. Okay, so we've eliminated that entry, and then let's move this to a new page. And then the entry in the third row. Okay. Now, notice that if I take this row and multiply it by -3, then I will get this row. So when I perform the next row operation, I'm going to have a row of zeros here. Okay. Whoops. Oh, sorry. First, I divided them to make the entries 1. And now it's even more obvious that the second row is going to cancel out the third one. So now we have a row of all zeros. So here are pivot positions, the 4 here and the 1 here. So x3 and x4, these columns do not have pivot positions. So these are the free variables. So we could choose anything, but we need a non-zero solution. That means we cannot choose both x3 and x4 to be 0. As long as one of them is non-zero, then we're good. Now, to match the answer that MyLabs happened to find for this problem. I just made these choices of x3 is 3 and x4 is 2. But you can choose anything as long as they're not both 0. Like I could choose this to be 0 and this to be 1, for example, and that would still give a viable solution. So then I just have to use these two equations to solve for x2 and x1 in terms of these prescribed values of x3 and x4. So first for x2, I'm working with this equation. So these terms, right, so I have minus 2x3 and then plus 5x4. So then I just fill in the values that I have, and I get 4. And then finally, for x1, same idea. So I have all these 3 terms, 3 minus 6 minus 3, all move to the other side. Note the sign changes. And then divided by 4 because of this entry here. So then I substitute what I have for x2, x3, x4, put all that in here, and I get 3. So now I have a solution. This vector x consisting of all the values that I have, x4, x3, x2, x1. Those give me a non-zero vector x that satisfies ax equals 0, therefore it's in the null space of A. Now, getting a vector in the column space of a given matrix is a whole lot easier because you can take a column space consists of all possible linear combinations of these columns. But any one of these columns by itself is a linear combination of the columns. It's just that all the coefficients are 0, and one of them, except for one of them, is equal to 1. So you can just choose a column, any column, and that would be a member of the column space. So in this case, I just here I just chose the first column. It should be column capital A. Okay. As long as that column's not 0, of course. All right. Now, the next problems, several of them, are all about given a collection of vectors, do they describe a basis of a vector space to come from? So however many components the vectors have, that's the vector space in question. So here we have 2 vectors of 2 components. Do we describe R2, or a basis for R2? Now, there's different ways of telling, like especially when you have 2 vectors. As long as the vectors are not parallel to one another, then they're linearly independent, and therefore they also span the space. These 2 vectors are not parallel. Also, if you put them as columns of a matrix, you can confirm that the matrix is invertible. And for a 2 by 2 especially, the easiest way to do that is to check their determinant, which I introduced last time. But the determinant would be minus 8 times 7 minus 2 times minus 64, and you would find that that's non-zero. But probably the easiest way is when you have 2 of the vectors is to check is one a multiple of the other. If not, then these make a invertible matrix. It is a basis. All right. Here we again have 2 vectors, are a basis for R2. Here they are parallel. If you take this vector, multiply it by 5, you get this vector. So if one vector is a scalar multiple of the other, then that cannot be a basis. Right, because for a matrix to be invertible, all the columns must be linearly independent, and also all the rows. Here we have 3 vectors. Do they form a basis for R3? So what you could do is if you assembled a matrix.
Can you go back to 4?
Yes.
Okay, I think I got it.
Okay. Yeah, so these 2 problems together illustrate the possibilities when you have 2 vectors. This is a multiple of this, not a basis. This is not a multiple of this, is a basis. All right. Here we have 3. If you made a matrix from these 3 columns, and you want to know if it's invertible. Now, what you can do is you can rearrange the rows. Once you've made a matrix, you can rearrange the rows. And what you would find is by scrambling rows, like if you make this bottom row of a first row, second row, third row, the matrix would be upper triangular. And in fact, what you'd be able to see that there's a pivot position in every row, every column. So just like row swapping, no other row operations needed. You find pivot positions in every row and column. These vectors form an invertible matrix, therefore it is a basis. Now here it worked out nicely because we had these 0 entries here. If these were non-zero, then you might not be able to tell just by looking or just by swapping rows that it's invertible. It may not be obvious. So what you would do in that case is you can try row operations and go towards echelon form. So if you can get the matrix in echelon form and you find pivot position in every row and column, again, it's invertible, therefore the columns do form a basis. Now, back to this problem real quick. This is a case of just 2 vectors. What if you had more than 2 vectors? So you have vectors from Rn, and you want to know if it's a basis for Rn. If you can see that any 2 of the vectors are parallel, like any vector is a scalar multiple of another vector, that's a deal breaker. The vectors are not linearly independent, therefore they cannot form a basis. Or you might see that maybe a vector is clearly the sum or difference of 2 other vectors. Again, a deal breaker. Because if you could express any vector in a set as a linear combination of other vectors, they're not linearly independent. So it wouldn't be a basis. Now, the number of vectors is important. I mentioned that the basis for Rn, any basis has to have the same number of elements, n. So for this one here, you can't make a basis for R3 with only 2 vectors. You have to have 3 of them. So these vectors would be linearly independent. So that's one criterion, but they do not meet the other criterion that they span a space, because it's not possible for 2 vectors to span a 3-dimensional space. So that's one way to quickly rule out a set of vectors being a basis, if it simply has a wrong number of elements. So here we do not have enough. Whereas in this last one, there are too many. So these vectors, in all likelihood, span the space R3. But because we have vectors that are only 3-dimensional, but we have 4 of them, there's no way that this set of vectors is linearly independent. because in an n-dimensional space, the most number of vectors that you can have that are linearly dependent is n. Anything else is, above that is going to be redundant. And besides, for a set of vectors to form a basis, they have to form the columns of an invertible matrix. An invertible matrix must be square. Here we have too few columns. Here we have too few rows, or too many columns. All right. So those are different ways of determining whether a given set of vectors forms the basis for its space. So once you've ensured at least you have the right number of vectors, so n vectors for n-dimensional space, in some cases you can check something like this, like is one vector clearly a linear combination of other ones, to rule it out as a basis. If there's nothing obvious like that jumps out at you, then the fallback is to do some kind of row operation. So here, row interchanges are enough to determine that this set of vectors does form a basis. Last resort, use elimination to use those kind of row operations to find the echelon form of a matrix. If it has a pivot position in every row, and therefore also a column, it is an invertible matrix. It is a basis. One example of a basis that we had seen before, it's called a standard basis. It's all the columns of the identity matrix. I'll just put this here. Standard basis for Rn, which is the columns of the n by n identity matrix. Come on. I think I stressed it out by typing too fast. But it had better recover. Come on, dang thing. Need to make sure that whatever I've typed into the file so far has at least been saved. Oh, it hasn't. Okay. I'm trying to, you can't see this, but I'm trying to edit this through another application. Just so I don't lose anything. Use the standard basis. I think I'm going to have to kill this application.
You're not anymore.
Sorry, what?
You're not screen anymore.
Yeah, that's intentional because I killed the application. I'm gonna bring it back in just a second. And it wouldn't stop hanging, so I had no other choice. Okay. All right. That is, as we've seen before, when I defined it, the standard basis is just the columns of the identity matrix. So these vectors that have elements that are all zeros except for EJ, the jth element is equal to 1. Okay. So, and we've seen how any vector in Rn can be described as a linear combination of these. If I have a vector in Rn, like as components x1, x2, etc., then I could take x1 e1 plus x2 e2 and so forth down to xn en, and so I've described my vector x as a linear combination of these. So it definitely spans a space. Also, there's no way to linearly combine these vectors to get to zero vector, except in a trivial way by using coefficients of 0. So they're linearly independent. So this is the simplest example of a basis for Rn, but any vector space has infinitely many possibilities for a basis. So for R3, any three vectors you can come up with that are linearly independent would describe a basis. So are there any questions about the problems that we've seen here dealing with bases and also the column space and null space? We leave only one section left, which I'll cover on Monday, and then you'll have the next Wednesday, a week from today, will be the review for test 2. But if you haven't looked at the practice test yet, I encourage you to do so fairly soon. You'll be able to do most of the problems on this point. I think it's only one problem chosen from section 2.9 that I haven't covered yet. Everything else, you've seen the material to do. And then I'll talk about that more next Wednesday. So, all right, I see that one of you is leaving already, but yes, I'm wrapping up. So I will stop recording at this point and stick around in case anyone has questions.